Okay, so there's the message. Hopefully Elizabeth will tell me what the link is.
Yeah, I saw it.
There it is.
I copied it to the
Oh, you got the link? Okay.
chat room.
Yep, that's it. I assume, Elizabeth, that'll be different every day, right?
Yes.
Okay.
But it can always be found on the NCAR CGD homepage, and it'll
Right.
show up at the top because it's one of the most recent recordings.
Okay, great. And should we record it as well, or is that not necessary?
Yes. Yep. I put that in the chat for you. I'll go ahead and hit that now.
Okay. Or I can do it either one if you want me to do it.
Sure. Sure. Yeah.
Okay, I'll do it.
Anyone who's a co-host gets the link.
Okay. All right, so it's being recorded too. And
You guys have a clock that can go on Zoom? I mean, I know there's an app.
I don't think we actually have a clock.
Right.
I don't know if that exists. If somebody could find one, that'd be great. Just put it in the chat. And then, so I'll call this out now before we start. So, well, actually, I'll call it out in the discussions. But Steve, I don't have a poster slide from you, I don't think.
No, I'm not going to have one.
You won't have one, okay.
No.
And I don't know if Jan.
Yeah, I think Steven sent an email to me. I updated the agenda.
Okay, fine. Where is the update? You have it on the website, Mingwei, the updated agenda? Or you just have it?
No, he sent it out on Thursday. Yeah, the order is different this morning than the original one too. So it's important to have it.
Okay.
At least for me.
All right. Yes. Okay. I'll go. I thought I had the most recent one from May 4th, but maybe it's a May 5th one. Well, let's see. That's great. We're up to 67 people. So maybe we should go ahead and get started so we can stay on time. Is that okay, Mingwei, or do you want to wait?
Yeah, I think go ahead, probably because it's already.
Okay. So I will share my screen and present. So welcome everybody on behalf of Danny and Mingwei and the rest of the ACPC group. I was just going to give a couple of welcome introductions and basically code of conduct, some things of what we're going to do for this meeting. And then I'm going to pass it off to Danny Mingwei, and then we'll actually get started. So welcome back to Virtual NCAR. Thanks very much to Elizabeth Faircloth, who's helped us behind the scenes do a lot of the organization for this meeting. We're trying some different things 2 years into the pandemic. We've learned a lot, hopefully, but obviously we've also learned that things are not going to go exactly as we planned. So we're trying for all those eventualities, but we'll see what happens. So there's a great program, and great to see so many people here this morning, this afternoon, and this evening. So just since NCAR is hosting the meeting, here's a little code of conduct. Basically, we value and respectful dialogue. So please follow all these things, share the air, let others talk, consider new ideas, acknowledge everybody's innovation, and offer constructive feedback. All those things that we learned in our first years of kindergarten or school, we should be doing here. Modalities. As I said, we should be good at this by now, but obviously things will probably go wrong. So we've tried to accommodate that. So Zoom, first of all, you got here, so that's about half the battle. Please, of course, mute yourself if you're not talking. And then as far as interactions, you can raise your hand. That's under, where is it? It's under, should be under reactions, basically, I think. the moderator, and moderator will select comments from people when it's appropriate, or you can put your question in the chat and the moderators will bring those to the floor, or the chat will continue on with discussion and speakers can answer things in the chat as well. Speakers should be enabled to share your screen. If it does not work, we're just going to immediately switch to the version that was sent. We have people on standby. That was the reason for sending in your talks. So if you haven't sent in your talks for the next couple of days, please get those uploaded to the website. If you don't have the link, or we'll send out another email or make sure that link gets in the chat as well. That will just facilitate that if your screen isn't working, you don't have to exit, reboot, do whatever. We will just have somebody else share your slides and you can tell them to advance. Poster summaries. Similarly, the way we're going to do the poster summaries, we're going to use one slide deck pre-assembled. We've got almost all of that together for today, I see. And then as we go through that, please be ready and unmute just before your time so we can go through that and try to stay on time. So as people have gathered, the modalities for the poster session, we're going to try something a little different. The poster presentations, we're going to have breakout rooms for every single poster under everybody's name. So there's going to be something like 10 to 14 breakout rooms. You will be able to move between breakout rooms, and there will be an opportunity to test this right before the break today, where I'll set up a couple of breakout rooms and we'll kind of show you how to do it. Those who have posters, you can go to your own breakout room. Those who do not have posters, as we go through the summaries, please think about maybe 2 posters you want to visit. Each poster session will have sort of 2 time blocks. We'll send out a announcement after 15 minutes to encourage people to basically switch. So what we want you to do is we'd like you to go to 1 poster, and then the presenter will have a short, hopefully 5-minute talk or less. And then there can be time for discussion with anybody in the room. And then we'll announce 15 minutes are up and we'll encourage everybody to switch. So then we'll do it again. So everybody can look at 2 posters. If a poster room is really crowded and somebody else does not have anyone present, feel free to switch rooms so that everybody has some people to talk to, and so we all spread around. And then we'll demonstrate this just before the break. In Zoom, you can actually control your own breakout. We'll set it up so you can move between breakout rooms. The only tricky part with that is you have to remember to leave the breakout room, not the meeting. It's really easy to kick yourself out of the meeting, but you can come back in. And we'll have a moderator in the main room to help direct people. So if at any time you're lost, you can come back to the main room. We'll figure it out. But we'll test that for everybody. And that, I think, is all I had to say. And I think I'm going to turn it over at this point to, I think Danny wanted to make some comments.
Yes. First, I would like to thank you and Andrew and Mike Jensen and Matt Christensen and Joanne Fan for organizing the agenda and this meeting. And I would like to welcome everyone. We have strong participation of 64 presentations and posters. Compared to last year, it was 63, so we are maintaining and even somewhat growing. Hopefully, next year, the ACPC meeting will be in person, at least in part. I'm not sure that everybody will be able to travel, but we'll have to see how it goes. But this is the way that I'm thinking about it presently. ACPC is a mission-oriented initiative trying to facilitate the quantification of aerosol cloud-mediated forcing, not only on radiation, but also on other atmospheric properties. And a major achievement of ACPC has been so far the realization of tracer, which has been a vision of ACPC, which is happening now. So I would like very much to thank Mike Jensen, who has very instrumental in that. Actually, he is the PI of the tracer project that got funded by the DOE. So with that, let's the workshop begin. Let's the games begin.
Okay, my name is Steve Kruger, and I will be moderating this session. There's 12 minutes per talk, I presume we'll run it with 10 minutes for your talk and then 2 minutes for questions. And I'll try to give you a 2-minute warning. So our first speaker is Sandeep Powell, and you'll see his title here, but I'll read it while he's getting set up. Connecting dots among synoptic controls, aerosol transport, and local meteorological conditions favoring cloud formation. Okay, we're seeing your whole presenter mode. Can you go full screen?
Yeah.
I think. Nope, I think it's the one where you had it with the 2 screen. There you go.
Right? Yeah. I did that, but I think it's some setup changed actually.
Okay, so
you need to click the other symbol to the left of this symbol that you clicked, like
right, the one that has the screen with the dashed.
This one?
Is that it, or is it we'll keep going over? Usually it's on the top, but otherwise it's under display settings at the top.
Okay, hold on a second. Yeah, I see that.
There. Nope, top one, swap.
Yeah, got it. Thank you.
There you go.
Yep. We think we know everything about Zoom, but we don't, right? So thank you very much, everyone. Good something, morning, evening, and afternoon all over the world. So as the title speaks about the connecting dots, it's connecting. So we are working on it. It's basically going to the synoptic controls, aerosol transport, and local meteorological conditions itself. And so basically, first of all, I would like to acknowledge my students who work here, Nicholas Clark, Michael Anand, and Matthew Hamill, who has been putting a lot of effort here on this particular part, but it's pretty much undergoing work, ongoing work itself. And acknowledge the Texas Tech University, startup funds for the work that have the purchase of the instruments and so on, and also other colleagues who actually contributed to one way or the other in the setup of the work. So thank you for this session. I would like to also thank the organizers for the ACPC meetings and also hard work behind the scene, whoever is involved here. Thank you very much. So as we know, the atmospheric boundary layer aerosols actually comprises of many different types of boundary layer scenarios. As we do not have to define what the boundary layer is in this session, but one of the prime major driver of the boundary layer forcing itself is that goes into the types of the boundary layer, moist or entrainment drying boundary layer, regimes of the boundary layer, and spatial interfaces of the boundary layer. That goes all along, and that's pretty much a schematic that I took it from the Stahl's book, but I made it myself. And so that's one thing remains pretty much that in the part of the aerosols portion itself is the aerosols in the arid region. That's basically think about this map of the reviews of geophysics book here with respect to the arid region map. And one of the prime factor for the arid region is the driving factor for the sensible heat flux, that is actually the very warm and the dryness of the region. And that has a big implication for atmospheric land atmospheric interactions, dry land expansion, and desertification and adaptations. Overall, the climate change acceleration that has been happening. So that's a big picture with respect to the arid region itself, because the land surface forcing is pretty complicated because of the low soil moisture regime in this region. So what I did actually, the NASA report, last one, 2018, that I went to the whole report itself and basically gone through the, eminent expert in the field. And what I actually did was search for the deserts, dry land, arid region, aridity. These are the keywords I searched. The answer was 0. That means the deserts or arid region boundary layer aerosols contains has been not giving a high priority to the boundary layer research itself. So that is the first starting point of the research I have been working here in Texas Tech. Atmospheric boundary layer research over arid domains, I call it ABL road. That's pretty much everything happens in the arid region. And now the dust particles, aerosols, the cloud formation is part of it. That I'd like to highlight some of the work in the way I've been doing here. So this is an example from our building that you can see on November 24, there's a dust layer was actually driven by the dry line. It was passing, and that's pretty much 2:11 p.m. and after 2:26 p.m. And that's within 10 to 15 minutes that the entire atmosphere changes so drastically. These are the strong, very thin layer of changes that actually happens by the frequent passage of the dry line throughout the year, most frequently in the springtime. So that's pretty much the whole idea. Now there's the aerosols here. We have a lot of implications for the cloud radiation feedback process and also the convection initiations and so on. This is pretty much a strong test bed for studying aerosols on this particular part of the synaptic control environment. So why do we care? Because of all these type of flows, local scale flows, mesoscale flows, and synaptic scale flows, they actually interact with each other, and then you basically come up with the one atmosphere that is all the scales are. Now what we need to do is that making measurements over different scales, which is also impossible except the campaign mode operations. So we kind of try to complement from the regular radiosondes, regular measurements, as well as routine LiDAR measurements as well. That's pretty much the whole regional scale versus local scale flows we try to capture here in this region. So if you think about like 3 to 4 extreme scenarios on the boundary layer aerosol part, one comes to the urban-rural interface, land-sea interface. For instance, urban-rural interface, you have basically tracer kind of field campaign pretty much driving factor. Now land-sea interface as well, tracer is giving a big importance on that. Complex terrain and adjacent planes, people have been working for elevated mixed layer. And fourth one is the frontal environment. This work is basically, we are working on the frontal environment itself. So how weather system modify aerosols in the boundary layer features and vice versa. So what we are missing, an impact of one another mass on the local boundary layer process as well. So, there's a lot of text here, but mainly we would like to say one thing here, that this is the location of our station here, the Texas Tech University, that is actually the interface of the humid and the dry air masses. So this work will benefit the development of new advanced ABL parameterizations and provide empirical data for intermittent processes over the arid region. That's pretty much the main driving factor of the work that we have been working on. So when you go for the, for the soil wetness with respect to arid region, there are multiple factors come into play. For instance, the average relationship with omega difference that it basically calls for a dimensional measure of the soil moisture precipitation coupling that goes down itself with the soil wetness, while the evaporation also pretty much increases as you go for the soil wetness itself increasing. So this is the part actually we are sitting here, that region of the high omega difference as well as the low soil wetness and the very low evaporation. And this actually has a pretty much strong implication for the cloud aerosol feedback processes and also the radiation feedback process itself. So what we are trying to understand that how these different types of land surface forcing under different types of synaptic condition vary and make the influence on the aerosol mixing in the boundary. That's pretty much 3 dots we're trying to connect. So this is the textbook picture. We all are of it, for the cyclogenesis with basically the Gulf of Mexico airflow, the steep lapse of the mountains and the adjacent plains there of the highlands, and that basically makes the whole convection initiation in this region. However, what is missing though, what happens exactly at the top of the boundary layer, basically at the internment zone process for the shallow clouds formation, that has not been documented well in this kind of scenario itself. So that was the part we started looking at. So this is actually, we started within this regional framework with the National Weather Service, radiosonde location, Emerald and Midland. What we actually see in this kind of synaptic environment, a myriad of situation that is basically AML, the elevated mixed layer from of the plateaus, and ABL interact sometime, and then the ABL and the EML, they mix together itself on the dryland passage, and EML, elevated mixed layer and dryland come together during the frontal passage, and none of them happens. All this kind of scintil scenarios are actually associated with the dust transport, because we are sitting in that dry versus moist region in the center interface. So this is exactly the scenarios I said for the one of the station, let's say, when the boundary layer and the elevated mixed layer, they are remaining separated from each other. And then when boundary layer, elevated mixed layer, they are trying to merge with each other. And then when they have completely merged. And these 3 scenarios have a strong implications for the dust transport in the region. But these are the snapshot of the atmosphere by, pretty much with this once a day or twice a day radiosonde launch. It doesn't give you what happens in this particular dynamical region itself. So that basically what we missed was document the internment zone processing that the interface of the high resolution data. So that comes the Doppler LiDAR measurements here that basically gives the UVW measurements, aerosol backscatter, turbulence features, and boundary layer depth estimation itself. And this is a snapshot of the pretty much for a very recent measurement, 2nd May. You can see from morning to the late afternoon, the particle velocity field as well as aerosol field from a ground to 6 kilometer height. And this is the basic indication of the boundary layer depth development is the yellow line here. And what you clearly see is this line is actually the time when the dry line was passing around 11 a.m. in the local time here. That actually the dry line passage was implemented by the around 40 degree Fahrenheit dew point drop. I mean 45 degree Fahrenheit dew point drop happened very instantaneously with the span of 30 minutes. And this dry line passage actually brought up a lot of aerosols in the region as well as the boundary layer development was pretty distinctly different. You can see before the dry land and after the dry land. What happens as the dry air mass comes is basically make the turbulence pretty much dominant, and you can see that whole vertical velocity field change drastically within 10 to 15 minutes field. So these are the assets of the measurements we have here. What we can do though, that if you think about the classical picture of the entrainment process, which basically drives the boundary layer versus free atmosphere mixing, and you think about the the humidity variance, that is basically the humidity, aerosol, there's all the variability. I don't mean the concentration. The variability is actually maximum at the top of the boundary layer where the clouds form. And this is basically from the water vapor variance that I worked in another paper with other people here. And this is the vertical velocity variance. What you can see, this is the active region where the boundary layer top is actually maintained. So keep that in mind. This part is the entrainment zone. Basically, we know all about. Or what we are trying to understand.
2 minutes left.
Right. During this shape, how does this whole thing works? So this is the preliminary results here for the frontal passage that we actually captured the data. What was astonishing was this, that during this frontal passage here at that 6 p.m. in the evening, that we can see a strong dust layer moved along the frontal boundary itself. And before this picture, I did not have a very strong documented frontal lift mechanism of the aerosols. And now you see in the clear picture next one at 6 p.m. This part of the data in more zoomed in version, that you can see this is basically the backscatter particles aerosol, and this is all the dust went up to the pretty much instant lifting of the dust went up to 1.2 kilometers from the ground, and that has been maintained around a 600-meter depth of aerosol, the dust cloud, for more than 1.5 hours, and then you had to stop the measurements because of the safety of the people and also many other factors that come into play. So that's pretty much the whole idea, that how does the dust transport happens during the synoptic scale process. Now you will be wondering that how can I actually determine that how does the lifting is happening, because this region we also have the vertical velocity field from the same lidar, that you can see with the vertical velocity up to more than 5 meters per second was observed exactly at the same time with the same lidar, that makes the whole lifting of the aerosol features in exactly the time, and that the boundary layer remain dynamic for a long time, more than 1.5 hours in the dust region itself. So this is basically the preliminary understanding of the entrainment zone processes. We are making the variance of the highest variability happens at the top of the boundary layer and the different times of the day, except this peak where the dust transport exactly happened during the frontal passage. And then, basically looking at the different types of dynamics in the entrainment zone, we want to try to make the connection between the entrainment zone thickness and the variability of the.
Okay, your time is up. So can you please wrap it up?
Yes. So basically, conceptual framework has been developed with the synoptic scale processes. We would like to see the impact of dryland passage, and have lidar measurements help elucidate the complexities. And a new framework has been also established for the aerosol mixing process. Thank you.
Okay, thank you very much. If there's a quick question. Anyone see any hands?
Can you say how this is different from the Haboob situation, where you have a gust front moving forward from a squall line? What are the differences?
This is exactly the pointer of that whether we define this as a Haboob or not, that basically is in the corridor we are actually working on, because we need to work on the aerosol optical depth changes around this time. This is very similar to the Haboob, what was maintained for 500-meter depth for more than 1.5 hours. Yes, very similar.
Okay, all right, great. Okay, I think we need to move on to our next speaker. Thank you, Sandeep. Okay, our next speaker is Rachel Sansom, and the title is Exploring a Stratocumulus to Cumulus Transition, a Perturbed Parameter Ensemble of Large Eddy Simulations.
Hello, can you see my screen?
Yes. If you could make it full screen, that would be great.
Can you see that now?
We can, it's still in the navigator mode. If you can go up there to the slide show and then click on.
Click this where I annotated.
Okay, one sec.
We'll just have to proceed with it how you had it. Okay.
Okay.
So we don't see anything right now, though.
Okay,
So-
can you see now?
Yeah, we'll just proceed as it is now.
Sorry,
Thank
it's
you.
coming up on my other screen. Yeah, so I'm going to be showing this work on stratocumulus to cumulus transitions that I've been doing using a perturbed parameter ensemble of large eddy simulations. This is with Ken Carslaw and Lindsay Lee and Jill and Leighton at the University of Leeds. So yeah, I'll just introduce stratocumulus to cumulus transitions quickly, and then how I've created a base simulation and the parameters that I perturbed from that, and then first kind of results of this time taken to transition. So I'm just looking at the Northeast Pacific, where you have this transition from kind of homogeneous stratocumulus decks to broken cumulus going from the west coast of the United States to Hawaii. So the kind of widely accepted mechanism for this is that it's caused by the increasing sea surface temperatures as the air is advected towards the equator. So as you're moving over the warmer temperature, the warmer ocean temperatures, then the turbulence becomes more surface driven and the boundary layer deepens and you get this decoupling. And the stratocumulus layer is kind of cut off from the ocean as a moisture source, and then is broken up by kind of increased entrainment from cumulus plumes, which leaves this cumulus regime. So this paper from Yamaguchi, Feingold, and Kaziel from 2017 found that for cases with lower aerosol, there could be this earlier transition. So this is showing cloud fraction and rainwater path. So you can see the simulations with lower aerosol is this blue and green versus the higher aerosol in red and orange. And they almost transition a full day ahead of the red and orange simulations. And importantly, they used a microphysics scheme here, which actually allows the aerosol to grow in cloud through collision coalescence, which allows this kind of positive feedback in the rain, where it's depleting the stratocumulus layer of moisture and aerosol. And then that causes more rain as well. So you get this kind of runaway feedback. So I've been interested in under which atmospheric conditions this can occur. So I started with a general base case from Sandu and Stevens 2011 composite transition. So I'm using the Monk LES model with a bulk 2-moment microphysics scheme called Casim. My horizontal grid is 50 meters resolution and it's 13 by 13 kilometers in the domain. And then the vertical layers are varying between 20 meters and 5 meters at the inversion, up to 3 kilometers. And again, we've got this aerosol processing where the aerosol can grow within the cloud, which means we can have that kind of rain feedback. So this is just animation of that base case. Sorry, it's a little small on the axes, but this left figure is the cross section through the cloud of cloud liquid water. Then in the middle, we've got liquid water path as a top-down view. And then on the right, there's the liquid water path and rainwater path time series, and then the cloud fraction time series as well. So you can see at the beginning, it's quite uniform stratocumulus cloud that persists throughout the day. And in the second day, it kind of thins a bit, but it recovers through the night. And then on the third day, it makes this transition to a more cumulus-like regime. So then from that base case, then I've perturbed 6 initial conditions simultaneously. So this is just showing kind of visually what those are. On the left is the potential temperature vertical profile. In the middle is the vapor mass mixing ratio. And on the right is the aerosol concentration. So the black line shows the profile for the base simulation, and then the orange and blue, purple show how that's been perturbed for the 60 simulations in this ensemble. So it's perturbing this boundary layer moisture and depth, the change in potential temperature at the inversion, the change in boundary layer moisture at the inversion, and the aerosol concentration kind of below the inversion. And then also there's the sixth parameter, which is the B parameter in the auto conversion equation from the Karuk-Danov and Kogan 2000 parameterization. So I've just kind of shown that as kind of high or low here, with values towards minus 1.3 corresponding to higher auto conversion rate. So then just to look at what that, how those are kind of spaced out in 6 dimensions. So this is a pairwise plot, and it's just showing kind of combinations of 2 dimensions at a time. So for example, at the top here, you've got the boundary layer depth on the y-axis and the boundary layer moisture on the x-axis. And then this is showing all the combinations down to the B parameter on the y-axis here and the boundary layer aerosol concentration on the x-axis. So you can see that these are well spaced out in those 6 dimensions. So then I'm just showing here the time taken to transition from stratocumulus to cumulus regime for each of those 60 simulations. So the yellow points are simulations that didn't transition within those 3 days. And then the dark blue points are ones that transitioned in under 10 hours. And then you've got the gradient between those. So if I just take this kind of yellow point as an example, and you can see its location or its kind of value in each of the ranges of those parameters. Then you can see this is just the animation, like with the first one I showed. It's very uniform stratocumulus throughout the whole 3 days. I'll just skip ahead of it. It starts to thin a bit in the 3rd day, but it kind of recovers through the night. And this might have transitioned if we'd been kind of simulating another day or 2. Then looking at one that's kind of 40 or 50 hour transition, you can see this is much more affected by the solar cycle. So kind of the cloud fraction breaks up quite a bit each day, but it does recover until the 3rd day when it breaks up and it doesn't recover again. And this does have a bit of drizzle, but it doesn't seem to have too much of an impact. Then finally, if we look at a very dark simulation, so a very fast transition, now this takes the 1st day to kind of produce stratocumulus, but then there's this very early onset heavy drizzle, and then this very quickly transitions to a cumulus regime, and it doesn't recover for the rest of the simulation. So then just looking at the behavior across the whole parameter space, it's quite reassuring that we can see the in this kind of row and column here, delta theta is quite important, which has been found in other studies, that the lower tropospheric stability is very influential on the time to transition. So you can see for weaker inversions, they're much more likely to transition than for stronger inversions. And as well in the kind of initial inversion height, the higher inversions are more likely to transition as well versus the lower inversion heights. But then interestingly, you can see that in this row and plot here, that the aerosol concentration has got a really strong influence on this time to transition, with lower aerosol concentrations producing much faster transitions versus higher aerosol concentrations. And this plot in the bottom right is showing the aerosol concentration versus that B parameter. And you can see as well that that autoconversion rate has a large influence too. And this is probably the kind of clearest gradient across any of these different plots. So it shows that these two are quite influential here on the timed transitions. So yeah, this is just looking at the stratocumulus transitions that cause a decrease in cloud coverage, and kind of assessing the aerosol rain influence that has previously been thought to be quite small, but the Yamaguchi paper found that it's actually quite influential, and it depends what kind of microphysics scheme is used. So I've used the perturbed parameter ensemble to assess the influence of this aerosol compared to other cloud controlling factors, and showing you here a kind of preliminary result on that time to transition. Thank you.
Hey, excellent timing. We have a couple minutes for questions. And if you can just speak up if no one's talking with the question.
Yeah, so can you hear me?
Yes.
So my question here is that, have you perturbed like the large scale vertical velocity or the SST gradient? Because those two seems to me more dominant forcing factors.
I've not done the large scale vertical velocity. I did consider it. And for the SST, I thought I would just leave that because it is just quite well known that that is the most kind of important factor, I suppose. So it's kind of looking at these secondary factors, I would say. I did consider the vertical velocity, but I haven't chosen to do that here. I was kind of not wanting to go much beyond 6 parameters, and these were the ones I chose. It's already quite hard to visualize.
Good, thank you. Yeah.
Thanks.
Other questions?
One in the chat.
Okay. How do the timescales for transition compare with any observations?
So I'm not comparing these directly with any observations. I would say, yeah, it's probably something I need to look into. So far, I've mostly just been comparing this with previous LES studies, and they compare reasonably well. I guess the fastest ones are probably faster than some previous LES simulations, but you have to kind of take into account that with all the combinations of the parameters, you might have some that aren't really kind of a realistic combination, but you know, generally the ranges do cover realistic ranges, but you just might have individual simulations that might occur much faster than anything you'd actually observe, if that makes sense.
Okay. Any other questions?
Yes, this is Graham. Can you hear me?
Yes, go ahead, Graham.
Yeah, Rachel, I wondered if you thought about the fact that there's a certain amount of covariability between some of the factors that you selected for this PPE, and whether that would sort of move you in the direction of a certain cluster of conditions, and that's where you might be thinking of comparing with observations.
Yeah, it's a good point. There's definitely covariability between them, and I would like to get to the point, as you say, of kind of, I guess the kind of next steps would be to start to split the parameter space into different regimes, and at that point we could probably compare those a bit easier with observations, I'd say.
Yeah, okay. Yeah, I think you've got a lot to further to look at here, and that's a great data set. So thank you. We'll move on to our next speaker. Okay, our next speaker is Jibo Zhang. Understanding the microphysical control and spatial temporal variability of warm rain probability using CloudSat and MODIS observations. Okay, you've got full screen. Thank you. So go ahead.
Hello, everyone. Thank you for giving me this chance to talk about our recent research, which is to understand the microphysical control and spatial temporal variability of warm ring probability using CloudSat and MODIS observation. Before I start, I would like to acknowledge my collaborator and also funding support. And this study has been just accepted in JRL and should come out in a week or two. So the focus of the study is the warm ring in marine low clouds. As we know, it is generated by collision coalescence process, which is much smaller than the typical grid scale of the GCM, so it has to be heavily parameterized. Warm rings is prevalent in marine low cloud. It is very important for the water budget in a marine low cloud, and therefore it is one of the important factors to determine the lifetime of marine low cloud and their radiative effects. And because of all these reasons, the simulation of warm ring is extremely important in the GCM. It is a determining factor for the lifetime effects and the aerosol cloud interaction. So from the measurement perspective, we can quantify the warm ring using the intensity, just as the millimeter per hour, the precipitation rate, or we can quantify it as a fraction of probability. So the quantify the precipitation rate is pretty difficult from remote sensing. We have to face many uncertainties, especially hydrometer particle size distribution. So that's why many previous studies propose to use the probability of precipitation to quantify the intense or likelihood of warm ring. And if you look at a typical radar curtain here, you can see anywhere if you have orange or reddish color in this cloud, marine low-level cloud, that's high likely that the cloud is precipitating. So by looking at the fraction of cloud, precipitate, that it is precipitating, we can know a lot about the cloud microphysics. So this is why many previous studies using POP to evaluate the models. And this is the early study by Wang et al. In 2012. They used CloudSat observations to look at dependence of POP on cloud water. This is liquid water pass. And you can see the increase with, you have more water, you have a higher probability of precipitation. And this factor can be classified into different aerosol loading and different stabilities. And by using these metrics, we can evaluate different models. This is a different version of models. And here, in our earlier study in 2018, we look at the map of the POP from a CloudSat and compare with LeCam 5, one version of LeCam simulations. And along with other studies, we found that warm ring is too frequent in the model. So this is just to show you POP is important and useful parameter. So in this study, we look at the POP dependence on two cloud properties. One is cloud liquid path, and the other one is cloud droplet concentration. So many previous studies have also looked at this, but the difference between this study and the previous ones is we want to test this key hypothesis. So basically, we want to show that we can decouple the grid mean POP into two factors. One is what we call the universal microphysical control. So we want to argue that if you have a cloud, and no matter whether it's in Pacific or Atlantic, as long as they have the similar liquid path and cloud drop concentration, they should have similar probability of precipitation. And then the grid mean POP can be understood by using this universal control and also the PDF of cloud properties. This is basically the sampling of the POP phase space. So to test this, we use the co-located MODIS and CloudSat observations. So the procedure is pretty simple. First, we use the MODIS observations to find the cloudy and the liquid phase cloud, and then we make sure it is low cloud. Then we use CloudSat data to find the maximum reflectivity in a column is larger than 15 dBz. This is a very typical and standard way to find the precipitating cloud from radar observations. And then we can define in certain region over a certain period, the probability of precipitation is basically the number of precipitating cloud divided by the total number of marine low clouds. And here are some results. First, we look at the total cloud fractions from MODIS, and then we look at the low cloud fraction. And we select these three regions with highest cloud fractions as our regional studies later. And here is the POP result. This is the probability of precipitation using the CloudSat and MODIS data. And you can see a clear transition from the stratocumulus region to the cumulus region, and we will come back to this point later. And these are the mean value of the liquid path in log scale and the cloud droplet concentration in log scale. Perhaps you wouldn't see too much dependence in this map. But if you change the perspective to this phase space, so here we plot the probability of precipitation as a function of x-axis liquid path and y-axis is cloud droplet concentration. So you can see at this corner we have large cloud liquid path and small cloud droplet concentration. So the probability of precipitation is pretty high, it's close to 1. And at this corner, we have a small liquid path and a large cloud droplet concentration. So we have a very small droplet, basically, and the probability of precipitation is pretty low. And by the way, this color map is based on all the population of the marine low clouds over the tropical ocean. And this white region is basically the sample is too small, so we ignore that. The white contour here shows the PDF. This is a PDF of the liquid path and cloud droplet concentration of all cloud over tropical ocean. You can see the mean value is around 90 some for cloud water, and droplet concentration around 60 to 70-ish. Yeah. So then we can we developed a simple parameterization using a logistic function to fit this color map. Basically, it's a function of the cloud water path and the cloud droplet concentration. It's a pretty simple fitting, but the result is pretty well. So here, this map here again is the POP from the data, and here is the POP based on parameterization. Basically, we use the universal POP derived from all the populations of the marine low clouds, and then we put this in this equation, and we use the PDF of cloud water and droplet concentration in each grade to predict the POP in that grade. And you can see that the grade with the observation pretty well, and the spatial correlation is around 93%. So this is a pretty encouraging result. And the next step, we want to understand whether this universal microphysical control can further understand help understand some spatial temporal variability. For example, here we studied the stratocumulus to cumulus transition in the Southeast Pacific region, and if we plot the Meridional average and look at the transition at the longitude, you can see pretty significant increase of the POP. It is red line. This is from data, red line, and it's pretty big increase. And if we look at the blue line here is the parameterization based on 2 parameters. So it's agreed with the red line pretty well. And then the question is, what is the reason for this transition? So we look at the 2 parameters. One is the cloud water path, the dashed line here, and the other one is cloud droplet concentration. So we want to know which one is more dominant. From here, we can argue the cloud droplet concentration perhaps is the dominating factor. So how to test that? So we use the 2 sensitivity studies. The first one is basic idea is if we keep one variable as a constant and only allow the other to vary from the coastal region to the open ocean, and see whether we can use that to fit the result. And if we fix the cloud water path and allow the cloud droplet concentration and change, and so this is the result. Or if we keep the cloud droplet concentration as a constant and allow the liquid path to change. And indeed, we can see if we fix the cloud water path and only allow cloud droplet concentration to change, we get this dashed solid curve. And if we keep the cloud droplet concentration as a constant and only allow the cloud liquid path to change, then we can get this dashed line. So you can see this one solid line agrees better with the observation, the right curve, and also the blue curve. If we allow both to vary. So similarly, we did this to look at the seasonal variation of POP. We look at 3 regions, but again, we are using the Southeast Pacific region as an example. So here we plot the seasonal variability of the domain average POP, and which give a red curve. You can see these peaks around the July and 8. And if we allow both parameters to vary, we get this blue curve here, and it's pretty well with the data. So that's just 2 parameterization. And then we did a similar trick. If we
2 minutes left now. That's all.
Okay. So if
try
we
to wrap up.
Okay, 1, 2. Liquid path change and cloud drop concentration change, and we can see the one with the liquid path change agrees better. The dashed line agrees better with the data and parameterization. So this is just sum up, and I think the most important lessons we learned is we can use 2-parameter liquid path and drop concentration and a very simple parameterization to explain most of the spatial temporal variability. And the idea is still decouple them into the microphysical control and the PDF of cloud water and the cloud drop concentration. Of course, this can be used in the future to evaluate the climate models, and the advantage of separating them is, we can look at both physics, the color map, or the PDF, whether the model has something wrong with the physics or have something wrong simulating the cloud properties. Of course, they are coupled, but I think there's a chance we can deeper in this if using this method. That's all. Thank you.
Okay, thank you. We have less than 1 minute left, so probably one question. And just go ahead and speak up to save me looking through the list.
So Steve, this is Andrew. I had a question I put in the chat. So the physical property for the microphysics, Yibo, it's very interesting. I like this. It's pretty cool. Physical property probably most related to precipitation is the drop size, not the number. So could you use that instead? Would you get the same result? And also, I'm happy to hand you some model output to do some comparisons for this. I think it's pretty interesting.
Yes. Yeah, we also look at the cloud effective radars, and we get pretty similar result. Just because, frankly, it's a GRL letter, we don't have enough space to put them, but we do look at effective radars, and they have similar result. Yeah.
Okay. Great, thank you. So in the interest of time, we're going to move ahead to the next talk. This one is by Xin Liu, adiabatic fraction of global marine boundary layer clouds decreases with temperature and height above cloud base. Xin Liu, are you here? I see you.
Okay, can you see my screen now?
Okay, we can see it. If you can make, your sound is not coming through too well, so go ahead and talk.
Okay, thank you.
Okay, we're not hearing you.
Okay, hello everyone. Xin Lu from Wuhan University. Today my topic is adiabatic friction retrieval of global marine bound layer clouds. My co-authors include Daniel, Feiyue, Yannian, and Zhengxin and Lingzang. Adiabatic friction reflects the degree of cloud mixing with the surrounding environment, so it's a very essential parameter for retrieval of cloud parameters. Now the cloud adiabatic assumption, that is by assuming adiabatic equal to 1, always lead to large uncertainties in the retrieval of cloud parameters, such as the cloud drop concentration and cloud geometric thickness. There are already some tentative studies for the retrieval of adiabatic friction based on the aircraft observations of the model simulations. However, those studies always only provide some limited data, so they are not sufficient for the regional or global climate change studies. And in this report, we will introduce an adiabatic friction retrieval method only based on the satellite observations and analyze the characteristics of adiabatic friction over the global ocean in detail. Adiabatic friction is defined as the ratio between the adiabatic measured liquid water path and the adiabatic retrieved liquid water path. The actually measured liquid water path can be provided by satellite observations, and in this study, we use it from the MODIS level 2 cloud liquid water path product. So the focus for the retrieval of adiabatic friction is on the retrieval of adiabatic liquid water path which is related to the condensation rate and the geometric thickness. The condensation rate can be calculated by the cloud top temperature and the cloud top pressure. So the core question is how to get the geometric thickness, because adiabatic liquid water pass is a parameter related to the second power of geometric thickness. If we want to retrieve an accurate adiabatic liquid water pass, we need to obtain an accurate geometric thickness firstly. So in this study, we retrieve the geometric thickness based on the Calypso LiDAR satellite observations, based on the method that we developed in our last work. By using the penetration and lowest cloud base and the corresponding highest cloud top, we can retrieve the geometric thickness for each 1 degree with the standard deviation of 160 meters. So in this way, we can retrieve the adiabatic liquid water pass with high accuracy. And in this way, we can obtain the adiabatic fraction over the global ocean. In this way, we retrieve the adiabatic fraction data over the global ocean in the year of 2014. And based on the 1-year data, we obtain the geometric distributions of adiabatic fraction and the geometric thickness. From the spatial distribution, we can see that the adiabatic fraction shows operative correlation with the latitude. The lower adiabatic fraction almost is distributed at the equator and the tropical Western Pacific, with the thick clouds and the higher sea surface temperature. And we also using the scatter plot between the adiabatic fraction and the geometric thickness to show some interesting results. With the increasing of geometric thickness, we can see that the averaged, the blue line shows the averaged adiabatic fraction, and decreasing almost exponentially with the increasing geometric thickness, and then stabilize at the adiabatic fraction close to 0.05. And we also compared our results with the adiabatic fraction retrieval method in other studies from Ming and Ephraim. The blue and the sign dots and the lines show the results in Ming and Ephraim. We can see that our results based on the satellite observations keeps a good agreement with the adiabatic fraction result based on the aircraft observations. Considering the operative correlation between the adiabatic fraction and the latitude, so we also make a analysis in detail for the dependence of adiabatic fraction and the temperature, including the sea surface temperature and the cloud-based temperature. The dependence of adiabatic fraction and the geometric thickness as a function of sea surface temperature shows that if we fix the sea surface temperature with the increasing of geometric thickness, the adiabatic fraction becomes lower. And if we fix the geometric thickness and the lower the sea surface temperature and the higher the adiabatic fraction. And we also get a relationship between the adiabatic fraction and the cloud-based temperature. We can see that the lower the cloud-based and the warmer the cloud-based temperature, the adiabatic fraction always getting lower. Those phenomena can be explained by the saturated vapor pressure, which is related to, operative related to the cloud-based temperature. A warmer cloud-based temperature always has a greater saturated vapor pressure, which also can consume more cloud water to saturate the entrainment surrounding air. So in this way, it will lead to a lower adiabatic friction under the warmer cloud-based temperature. And the last is a summary in brief. From the results, we know that adiabatic friction always decrease with the increasing cloud geometric thickness and stabilize when adiabatic friction close to 0.05. And from the relationship between adiabatic friction and the temperature, we know that adiabatic friction is highly dependent on the sea surface temperature and the cloud-based temperature. Adiabatic friction always increase with the cooler sea surface temperature and increase even more clearly with the cooler sea surface cloud-based temperature. And we also make another analysis between the adiabatic friction and other meteorology, including the relative humidity and the lower tropospheric stability. The results show that there are little dependence of the adiabatic friction and those other meteorology parameters. Okay, thank you.
Okay, thank you very much. We have time for some questions. We have about 2.5 minutes. Just go ahead and speak up.
I have a question. Thank you. That was very interesting. And I like the fact that you highlighted the importance of cloud-based temperature. I wonder whether in your adiabatic fraction retrieval, you are fixing the CW parameter, which of course is temperature dependent. So when you show the adiabatic fraction as a function of temperature, are you keeping the CW constant, or have you varied it?
Yes. Now we use the constant. No. Now we calculated the CW for each cloud by using the cloud by only using the cloud top temperature and the pressure. So they are different for different cloud.
Okay. I have a quick question. I would think that the CCN concentration would have some impact. Have you considered that?
Yes. Adiabatic friction always lead to the underestimation of the cloud drop concentration by using the cloud adiabatic assumption. So, but now in our result, we didn't show the result the influence of the adiabatic friction on the CCN. And the next we will do this. Yeah.
The question was different, whether the adiabatic fraction is affected by.
Right. The adiabatic fraction should be affected by the CCN concentration.
Yes.
Okay. Any other questions? Okay, thank you. We'll make up 15 seconds here. All right. Okay. Thank you very much. Okay, our next speaker is Zhou-Kun Liu, constraining the parameterization of autoconversion in marine stratocumulus by observations of their breakup due to precipitation.
Okay, thank you.
Go ahead.
And hello, everyone. This is Zhou-Kun speaking. I'm very happy to share my work again in this year's ACPC workshop. And today my topic is constraining the parameterization of autoconversion in marine stratocumulus by observations of their breakup due to precipitation. And many thanks to Minghui, Danny, and Yanning. As we know, the aerosol cloud interaction continues to be uncertain, and there is a large variety of the cloud lifetime effects among the climate models, so that it is important to constrain the warm marine parameterizations in models by the observations. We can see from the satellites that there is large dependence of the cloud fraction and the rain rate on the aerosols. So in our previous work, we derived the conversion rate from the cloud water to rainwater from the A-train satellites. And we use the susceptibility of conversion rate on the cloud droplet number concentration to constrain two different out-conversion schemes. We found that the beta parameter in out-conversion schemes is underestimated compared with the A-train satellites. In this work, we want to explore another approach to constrain the parameterization of the precipitation. We know the no clouds often exist as the closed cells. The clouds are nearly overcast and the cloud fraction is about 100%. Driven by the precipitation, the clouds begin to break up and they are transformed into the open cells. The continuous change of the cloud properties can be captured by the high-resolution geostationary satellites such as the several imager on board the MSG satellites. We think that it is a great opportunity to constrain the warm-rain parameterization by the observations of the breakup process of the closed cells from the Lagrange perspective. And another problem we found in our previous work is that in the KK2000 autoconversion scheme and some other schemes, the precipitation is less susceptible to the cloud effective radius compared with the A-train satellite. And the aircraft measurements have also found that the autoconversion rate is proportional to the fifth power of the droplet radius. So in this work, we want to test that if another form of the autoconversion parameterization in KK2000 can capture the transition process from closed cells to open cells, because it is defined by multiplying the amplitude parameter and the fifth power of droplet size. So in this work, we pick up the 3-day transition case over the Northeast Atlantic Ocean on the January 27th, 2010. The closed cells are located here, and after 2 days, the closed cells begin to break up. And some previous works have studied this case by the LES model. Here we use a high-split model to get the trajectory of the closed cells, and we can see the cells move to the southwest under the control of the high-pressure system. Here we use a Wolfram with a Morrison scheme to simulate this case. And as I said, we adopt another form of autoconversion parameterization from KK2000. Since we trust the fifth power relationship, the uncertainty comes from the amplitude parameter C, which can also control the autoconversion rate in this formula. So here we perturb the value of the C parameter to only a half of the default value and 1/10 of the default one. So after that, we compare the model results with theory and MODIS observations, so that to constrain the C parameter. After that, we conducted two different simulations with less chemical emissions. So here comes the results. Each dot here represents for the average cloud properties within 1 degree around the trajectory of the closed cell. We can see from the black dots, which stands for several observations, that the cloud fraction begins to decrease from 100% on the afternoon of January 29th. While in the default case, CE, and the case with only half of the amplitude parameter, the breakup happens about 24 hours earlier than the observations. When it comes to the 0.1C case, which is shown in light green, we can see that the time is delayed and it is comparable to several observations. We also found that the breakup often follows a sudden decrease of the cloud droplet number concentration and a sudden increase of cloud droplet effective radius, which proves that the precipitation drives the breakup. From the auto-conversion rate and the surface area rate, we can clearly see that the precipitation is delayed by decreasing the C parameter, so that the closed cells contain more water to precipitate on January 29th. We also found that the decrease in amplitude parameter also improved the relationship between cloud fraction and effective radius. In the observation, the cloud fraction decreased when effective radius increased to about 18 microns. 0.1 C represents it well, while it is not the case in the other two cases. The evolution of the relative PDFs of the effective radius are also improved in the 0.1 C case. From that, we can see there are more cloudy pixels with large effective radius in this case. So here we constrained the C parameter to the 0.1 times because it can better capture the breakup time of closed cells and the evolution of the cloud properties. If we decrease the chemical emissions to only 1/4, and we can see the cloud drop effective radius increase so that the precipitation initiates much earlier. The breakup happens much earlier too. The changes of the cloud radiative effects can be very large between the two cases because the changes in cloud fraction and nuclear amount is large. But what if we constrain the C parameter to 0.1 C? Will the changes in the cloud radiative effects increase or decreases? So here we calculated the changes of the CRE before and after the C parameter is constrained. So the numbers here represent for the daily average. We found that the changes in the cloud radiative effects decreased by about 30% over the region after the amplitude parameter is constrained to 0.1 C. We think that it mainly because a change in the cloud fraction becomes much smaller in the first 2 days. So in conclusion, here we constrained the amplitude parameter by the continuous observations on the breakup of the closed cells. The 0.1 C case simulated the evolution of cloud properties more properly. And if we decrease the C to 0.1, it weakens the changes in CRE by aerosols, and the changes in CRE decreased by about 30% over the whole area. So that is what I want to show today, and thanks. Hello?
Sorry, I was muted. We have plenty of time for questions. So if you have a question, go ahead. Well,
I would like just to make a remark, is Danny, that this paper actually shows highlights the importance of the cloud breakup to the radiative effect of the clouds and the sensitivity to the auto conversion parameterization. That is to encapsulate the conclusions.
Yes, yes. Thank you. Okay. Okay, well, let's thank you. Let's move on to the next talk then. So our next talk is by Tianning Su. Aerosol boundary layer interaction modulates the entrainment process. Go ahead, please. Thank you.
Thank you. Hi, everyone. I'm Tianning Su. I'm a postdoctor from University of Maryland. Today, I'm delighted to share our research about boundary layer entrainment and how it would respond to aerosol. To begin with, let me give a brief introduction by answering two questions. The first question is, what is boundary layer entrainment? We know the boundary layer, or PBL, can grow rapidly from morning to afternoon. Due to the PBL growth, air masses in the free atmosphere would be entrained into PBL. This process is called entrainment. The entrainment process takes place in the entrainment zone, which is located at PBL top. The second question is, why is entrainment so crucial for PBL? PBL is a chaotic system. This widely used figure demonstrates the complex interaction between multiple parameters. We can see the entrainment process is marked in the central position of the entire interactions. It is a key process to connect the whole diagram. The entrainment directly links with PBL turbulence, surface fluxes, and cloud development. Entrainment also controls the PBL growth and the energy exchange between free atmosphere and the PBL. Despite the complex system, our study focuses on three parameters, including PBL top, aerosol, and entrainment. There may be intertwined interaction between the three factors. The integrated interaction have not been well understood yet. To better understand this issue, let's look at how entrainment represents in a numerical models. The entrainment process links with PBL turbulence and cannot be mathematically solved. A linear parameterization is used to simplify this problem. In general, it assumes the turbulent heat fluxes within PBL are linearly distributed. So the entrainment fluxes at PBL top are proportionate to the surface sensible heat. However, it's still questionable whether this parameterization is valid for different situations, especially in a polluted environment. Bring with these open questions, we use comprehensive field observation over Beijing and real analysis data to study boundary layer entrainment. For the method part, we will use the PBL growth rate to estimate the entrainment rate. We adapted our previous method to retrieve PBL variations during the daytime. Our evaluation indicates this method can produce a good estimation of PBL growth rate. In this study, we do not consider cloud, but intend to include cloud in the future. With the method, let's look at two cases of PBL variation. The first is a clean case, and the second is a polluted case. The black line and the pink line indicate the PBL height retrieved from observation and the Aero5 reanalysis data, respectively. We can see the PBL deepens more rapid for the clean case. We also found the PBL height from reanalysis data is consistent with the observation for clean case, but the PBL from Aero5 is considerably overestimated under the polluted case. Such a difference between reanalysis data and observation is not limited by single case. By using 2-year observation, we can see the PBH from Aero5 is systematically overestimated under the polluted condition in Beijing. Meanwhile, the bias are largely caused by the inaccurate estimation of PBL growth. In other words, the bias are related to the PBL entrainment. To understand the mechanism, we need to calculate the aerosol radiative effects. The aerosol radiative effects are closely associated with aerosol vertical distribution. Therefore, we adapted our previous approach to classify aerosol vertical distribution into two categories, the decreasing aerosol structure and the inverse aerosol structure. We further used the radiative transfer model to calculate the aerosol radiative forcing. Compared to the decreasing structure, the inverse aerosol structure caused substantial heating in the upper PBL, further increased the PBL stability. To link the aerosol radiative forcing and the PBL turbulence with the K-closure theory. Basically, this theory tells us the change of heat fluxes can be approached by the change in the temperature gradient. Thus, we can quantitatively understand how aerosol heating effect in the atmosphere can change the PBL turbulence. The estimation of aerosol's impact on turbulence also involves the calculation of several parameters. I listed this equation, but we are not describe them one by one. Based on the classification, we present the entrainment rate under different aerosol structures and absorptions. Compared to the decreasing structure, the entrainment rate under the inverse structure is lower by about 80%. We also found that the Aero5 reanalysis data do not produce accurate entrainment rate under inverse structure, especially for absorbing cases. We believe the difference are related to the aerosol radiative effects. This figure presents the impacts of aerosol on heat fluxes at the up PBL. Under the inverse aerosol structure, abundant aerosol located at up PBL can significantly suppress the vertical heat fluxes. This effect can change the thermodynamic structure and lead to a reduction in entrainment at PBL top. We also examine the general relationship between entrainment rate and aerosol loading in the vertical. High correlation between entrainment rate and aerosol loading are found in the upper PBL. This relationship indicates an important interaction between aerosol and entrainment. We also compare the responses of entrainment rate to aerosol loading from different data sources. To limit the impact of sensible heat, we divided the data into 3 scenarios: the high sensible heat scenario, medium sensible heat scenario, and the low sensible heat scenario. We can calculate the entrainment rate using the linear scheme. It is indicating a linear relationship between sensible heat and the entrainment. The Aero5 also adopted a similar linear scheme in their parameterization. As a result, the entrainment rates from linear scheme and Aero5 do not strongly respond to the aerosol loading. In the contrast, the observed entrainment rate drastically decreased as aerosol loading increased. To minimize the change in meteorological background, we also removed the wind shear effect and constrained the sensible heat effect. Thus, the change in entrainment rate in the last video can be largely attributed to the aerosol effect. We have several bullet points to summarize the result. Aerosol can suppress the entrainment processes, especially for the inverse aerosol structure, and the mechanism of aerosol entrainment interaction can be a key ingredient for the air pollution formation. And the aerosol entrainment interaction can explain the great sensitivity of the observed entrainment rate to aerosol. Besides the mechanism, this study also caused a better entrainment parameterization under the polluted condition. Actually, we already have some preliminary analysis, and this study has some direct benefit for the entrainment parameterization. Based on the previous analysis, we summarize the responses of entrainment to PM2.5 under different sensible heat scenarios. Furthermore, we use the observed sensitivity to adjust the entrainment rate in Aero5 reanalysis data. The change in entrainment rate can lead to the decrease in PBLH under polluted condition. The pink line indicates the adjusted reanalysis data. We can see after adjusting the entrainment, we effectively remove the systematic bias between observations and the reanalysis data. However, this strategy is more like a general correction for the overall bias. We still hard to accurately estimate the entrainment rate for individual cases. So for the future directions, we propose to combine some empirical relationships and the deep learning technique to parameterize the entrainment in a polluted environment. I hope we can have some results to share with you in the future. Here is the conceptual scheme for our study. We already summarized the key points in the previous slide, and I want to repeat here. It generally indicates an important interaction between aerosol and entrainment, and we refer this interaction as aerosol entrainment coupling. Here is my talk. Thank you.
Okay. Thank you very much. So we're open for questions. We have a couple of minutes. Let's see what we have here. Okay, I'll read this one from we have a couple here. So from John Casel, can you comment on the role of large-scale subsidence for boundary layer height in the context of your observations?
Yes, exactly. We will use the large-scale substance from Aero5 reanalysis data to correct the entrainment rate in our observation. in general, for the fair weather conditions, the large scale substance is much smaller than the PBL growth rate. So the effect is not very strong. But under certain synoptic pattern, the large scale substance could play a very important role.
Okay. I'm reading another question from the comments. Nice work. How well do you think these results will generalize beyond the case of Beijing?
Yes, it is a very important question. We select the Beijing as the observational site is mainly because there's a rich aerosol and there's some severe air polluted condition. It will let us can clearly observe the aerosols impact. But if we take places in some clean region like SGP, like in the US, like in other clean region, we may not observe such drastic difference between polluted case and the clean case. But even for under the light polluted condition, aerosols still can play certain effect. That need very sensitive calculation to quantify that, and may not clearly observed in the observations.
Okay, I actually have a quick question. So I can see aerosols having two impacts. One is they would reduce the surface heating, surface sensible heat flux. They could also tend to stabilize the boundary layer by the heating profile of the aerosol absorption. Which of these is most important?
Yes, that is a key issue in our study. We jointly analysis the sensible heat and aerosol heating profiles. For the entrainment rate, we believe the second process, which means the aerosol vertical heating, is more important, especially for the absorbing cases. And because we can see under the inverse aerosol structure with absorbing cases, the entrainment rate is much lower. Meanwhile, the sensible heat do not show very strong exchange. For example, we see about 80% change in entrainment between the different aerosol structure, but the sensible heat only change about 20%. Okay. So the second process should be more important, but that depends on aerosol vertical structure and aerosol absorptions.
Yes, okay, great. All right, excellent. All right, thank you very much. We'll move on to our next speaker now. So our next speaker is Xiaoli Zhao, observational estimate of stratocumulus susceptibility across timescales. Okay, go ahead.
Hi, can you hear me and see my slides?
Yes, both.
Okay, great. Thank you. Hi, everyone. I'm Xiaoli, and I would like to share with you our recent study about observational estimates of cloud susceptibility across timescales. And this is an ongoing work. So the understanding of aerosol cloud interactions have been greatly improved over the past decade. And recently, one of the key questions that have brought our attention is its timescale. However, the studies in these regards are very limited at the moment. Franziska Glasmeyer and the co-authors did some pioneering work looking at the adjustment timescale of liquid paths to the perturbation in cloud droplet number using the nocturnal LDS simulations. And they found in their study that the adjustment timescale is about 20 hours. However, the consensus is not yet reached. For example, Ed Grisbeard et al. 2020 found almost near instant response of the liquid paths within ship checks. So clearly more research needed to be done to quantify the magnitude and trend of the liquid path adjustment. However, it's kind of difficult to do that from the observational perspective because it's hard to isolate the relationships between liquid path and the cloud droplet number due to the very common covariabilities with the meteorological conditions. So here we approach this problem by using the 1D wavelength analysis that we think can overcome these difficulties. The data set I will be presenting here in this talk is 17 years of our data from ERA5 and CAMS. I'm currently looking at ground-based and geostationary satellite measurements and retrievals, and I hope to share the results with you in the future. So for the data set to be used in the wavelength analysis, we need to construct time series first. Here we look at 8 degree by 8 degree box over the eastern North Atlantic Ocean. And at each hour, we compute the average values from the pixels of single layer warm boundary layer clouds with cloud fraction greater than 0.5. So we repeat this process every hour to get time series. Here, I'm showing you the time series of normalized liquid water paths over these 17 years on the top panel. And on the bottom panel is the corresponding wavelet power spectrum, with y-axis showing you the time scale. So the yellowish color indicates greater power, and greenish and bluish color indicates weaker power. And the black contour here shows the 95% confidence level. So we average the wavelet power in time, and we can get the time average wavelet spectrum, as you can see on the right. So here, whenever this wavelet spectrum is greater than the 95% confidence spectrum, then we consider the signal to be significant. For example, liquid path, as you can see here, has significant diurnal and seasonal variability. So we extend this analysis to other cloud properties, aerosol properties, and meteorological properties, and we can get fairly good understanding as to when significant variabilities will occur for each variables. Consistent with existing literature, there are 4 major variability timescales: diurnal, synoptic, seasonal, and annual, and we found weak variability beyond 1 year. So now let's focus on the aerosols showing on the third panel. You can see that apart from these very significant annual variabilities, aerosols also have significant variabilities on the synoptic scale, and the variability trend is very similar to that of the horizontal winds. So this confirms that the aerosols in that area, at least, are mostly caused by the wind advection related to the synoptic systems. So our strategy from now on is to investigate the cloud susceptibility seasonally. This time is long enough to cover the variability of aerosols. And specifically, I'll be showing you the results from June, July, August, where the stratocumulus clouds are mostly frequent. So here, let's take a deeper look and to see how often are the liquid paths and aerosols coherent and at what scale. So we get this information by applying wavelet coherent analysis between liquid paths and aerosols. And I'm showing you here an example for June, July, August 2010. So as you see, the contoured area indicates the time and the time scale when the liquid paths and aerosols are significantly coherent. However, note that the coherent here does not speak to the sign of the liquid path adjustment. It can be positive or it can be negative. It just tells us they're coherent. So using this information, we calculate the frequency of occurrence of significant coherence between liquid paths and aerosols across timescales in June, July, August over the entire 17 years. And we found almost 20% of the time, liquid paths and aerosols are coherent. But note that within this 20% of the time, there are also time periods where when the aerosols co-vary with meteorological conditions, and especially the horizontal winds, as I said before. So in order to evaluate the liquid path adjustments in the absence of meteorological conditions, here, we exclude the time periods with covariabilities between aerosols and meteorological conditions, and only keep the time periods with covariabilities between liquid paths and aerosols. And we call that time periods the clean time periods. Within the clean time periods, let me show you how we compute the liquid path adjustment. So here, I'm showing you the example of a 3-day case. This case this case is a very strong coherence between liquid paths and aerosols on a 3-day timescale, as you can see from the left 2 panels. And also you can see this noisy from other timescales. So in order to compute the clean liquid path adjustment, what we did is we decomposed the liquid paths and aerosols at this 3-day timescale. and use this decomposed value to compute the liquid path adjustment, as you can see on the right panel. So this way we can avoid the noise coming from other timescales. So this is just one case showing positive liquid path adjustment. We have other cases showing negative adjustment as well. So we put these calculated adjustments together. Here I'm showing you the statistics of liquid path adjustment across timescales in June, July, August over the entire 17 years. You see that although the data is a little bit noisy, but we can see overall there's the strongest negative cloud adjustment occurs at between 16 hours to about 1.5 days timescale, which is consistent with predicted by the nocturnal large eddy simulations. And the result holds even when I include the covariabilities between aerosols and winds. So the take-home message here is that we apply the wavelength analysis to evaluate the liquid path adjustment across time scales for the first time. And this approach can isolate the time periods with meteorological covariability removed. And we expect to have the results from ground-based and geostationary satellite retrievals very soon. Thank you.
Okay, thank you very much. We have time for questions. So please go ahead and put them in the chat or raise your hand or speak up.
Hi, Jolie, this is Rob. Is it okay for?
Yes, go ahead, Rob.
Yeah, really interesting analysis. I didn't catch everything you did, but were you able to see that the positive and negative adjustments occur under distinct meteorological conditions? You know, it's been argued that precipitation occurrence tends to favor positive liquid water path adjustments and non-precipitating negative. Did you see that?
The data that I am working on, the ERA5, is a little bit noisy. I hope I do see positive and negative, but not very strong signal. I hope to take another look at that using the ground-based and geostationary data.
Thank you. Thanks.
Yeah.
Other questions? Okay. Well, thank you very much. We'll move on, make up a little more time. So our next speaker is Fan Liu. This is the last one of this session. Contrasting large effects of fine and coarse aerosols on warm rain from marine clouds.
Can everyone hear me?
Yes.
Thank you.
And you can go to full screen, perhaps. There you go. Great. Go ahead.
Hello everyone. I'm Fan Liu from Wuhan University. In this presentation, I will show the first observational quantification results of the combined effects of fine aerosols and the caustic salt aerosols on warm cloud microstructure and warm rain. And the authorship are from Fei's team in Wuhan University, Danny and Zheng Xin in Hebrew University, and Yan Nian in Nanjing University. First is the research background. This figure shows warm rainfall over ocean is much more frequent than over land. And many previous studies also reported this natural phenomenon. However, it is still fully explained by the meteorological differences. While in this study, we will show the land-ocean warm rain contrast can be well explained by the unique nature of oceanic fine aerosols and the caustic salt aerosols. In this study, we focus on marine warm clouds, and the research area of our study is inside this red rectangle. And here is research background. And I will introduce data and the methodology of this work at here. Several data sources are used in our study. Cloud data was obtained from Meteosat geostationary satellite. Precipitation data was obtained from GPM dual frequency precipitation radar. Aerosol and the meteorology data were from MER2 and NSAP reanalysis data respectively. As this figure shows, all data are matched to 1 by 1 degree grids as samples. For data quality control, available samples should have no ice cloud in 1 by 1 degree grids to focus on only marine warm rain process. And because surface clutter always prevents radar from observing near surface rain, thus low clouds are eliminated in our study. And finally, we got about 60,000 rain samples and 40,000 non-rain samples from 4 years data. And next comes, here comes the results of our study. And first, as we know, aerosols usually co-vary with key environmental variables, and both of aerosol and meteorological conditions dominate cloud properties. In this page, LWP is fixed to isolate meteorological influence because atmospheric thermodynamic condition determines cloud-based property and cloud vertical development. Thus, LWP can capture much of meteorological variability. For this figure, the two rows represent fine aerosol and the Cauchy salt effect respectively, and the three columns represent RE, rainfall frequency, and the rainfall flux respectively. Different color from blue to red represent low to high LWP bins. From figures A to C, we can find only moderate suppression effects of fine aerosols on RE and the warm rainfall properties, while from figures D to F, only a very small Cauchy salt enhancement effects on RE and the warm rain are observed. However, it is not that the coexisted fine aerosol and Cauchy salt may offset each other's influence and lead to only small indicated sensitivity in this page. Therefore, next we will separate the mixed effects of fine aerosol and the Cauchy salt. Here, next page. Here in this page, Cauchy salt is fixed in order to focus on the fine aerosol effect. In this figure, x-axis represent fine aerosol concentration, and the different color from blue to red represent low to high Cauchy salt bins. And from these figures, we can see that stronger fine aerosol suppression effects on RE and the warm rain are found when Cauchy salt is fixed. And statistically, increasing fine aerosol decrease average RE by 11.4 micrometer, which is more significant than the result without fixing Cauchy salt. Additionally, for rainfall frequency and rainfall flux, we can find they decrease almost linearly with fine aerosol and is gradually stabilized after 2 microgram per cubic meters. And this page is fine aerosol effect. Next page, I will introduce Cauchy salt effect. Here in this page, fine aerosol is fixed in order to focus on Cauchy salt effect, and different color from blue to red represent low to high fine aerosol bins. From this figure, these figures a much stronger enhancement effect of Cauchy salt on warm rainfall properties is revealed after fixing fine aerosol. Also, statistically, RE continuously rises with increasing Cauchy salt by an average increment of 8.3, which is comparing to 0.9 micrometer without the fixed fine aerosols. Also, stronger Cauchy salt enhancing warm rain and frequency are revealed in these figures. Moreover, some typical meteorological parameters were also used to isolate meteorological variability in this study, and all results consistently indicate that the observed comparable but opposite effects of these two aerosol types are independent of the meteorological conditions. Finally, I would like to make a conclusion with this presentation. And statistic conclusions are included in this conceptual diagram, where panel A to B represent scarce fine aerosol to much fine aerosol condition, and the panel C to D represent scarce to much coarse sea salt condition. And the statistics of the average RE and the rainfall are listed in each panel, and the changes upon transition between states are marked by the arrows and the adjacent numbers. Well, from panel A to B, we found for fixed LWP and coarse sea salt, increasing fine aerosols decreased rainfall flux and RE by an average factor of 1/4 and 40% respectively. Conversely, from panel C to D, for fixed LWP and fine aerosols, added coarse sea salt enhanced rainfall flux and RE by an average factor of 4 and 35% respectively. In summary, we found the effects of fine aerosols and coarse sea salt on marine worm are opposite, comparable, and independent on meteorological conditions, and they tend to offset each other when both aerosol types coexisted. Moreover, abundant coarse sea salt over ocean increased the worm rain, and we think this can explain much of the land-ocean worm rain differences. And that's all my presentation today. Thank you for your kind attention.
Okay, thank you very much. So I see one comment in the chat. It's from Lauren Zamora. It might be interesting to see whether there is a vertical difference between effects you saw that were associated with coarse sea salt and fine aerosol, example using CloudSat. You might expect the coarse aerosol effects to be higher, closer to the surface. So that's a comment, not a question. So, but if you have any response to that, go ahead. Okay, we have another from Danny. We looked at that and the effect extends to cloud top. Okay. Are there other questions? It's a very interesting talk. I'm not sure I understand the coarse sea salt mechanism yet, but
I may, if I may add a few words about the mechanism. This is Danny.
Yes.
Coarse sea salt acts as a giant CCN. We took the radius larger than 1 micron or diameter larger than 2 micron from ERA2 data, okay, only for the sea salt, and that acts as a giant CCN. Also reduces the supersaturation at cloud base and inhibits activation of fine aerosols. And by that, by these two mechanisms, enhance the autoconversion and the warm rain. That's okay, the idea.
All right, great. Yes, thank you very much, Danny. That helps a lot. Other questions?
Can I just follow up to the question about the vertical effects?
Sure.
Yeah, so I was just curious. So Danny, you said that the effect extends to the cloud top. Does that mean did you look at clouds of different heights, like some that were closer to the surface and some at taller clouds, or can you explain?
Yes, there is a whole other work that Fadlu has been doing, looking at the DPR drop size and concentration as a function of cloud top height and the rain rate, and showed the effect of these two different aerosols on the raindrop size distributions, and we see the expected effects of sea salt shifting the drop size parallel vertically all the way to the height where rain rate is taper off at cloud top. So it's not limited only to the lower levels. So I infer from that that once the coarse aerosols are caught in the updraft that feeds the clouds, it goes all the way to the cloud top. And no wonder if there are only a few percent, the terminal fall velocity is negligible to the convective updraft speed.
Okay.
Okay, no, that's interesting. Thank you.
All right, great. Okay. Thanks to all the speakers this session. I'm going to turn back the session to Andrew, and he'll have some announcement on the rest of our schedule.
Thanks, Steve. Thanks to all the speakers, and thanks very much, Steve, for leading that session and giving us a very good overview and keeping everything moving and on time. We're going to do two things. First off, everybody please turn on their camera because we've got 95 people in the room. We're going to take a couple of pictures for the annual ACPC Zoom Smorgasbord chat or Zoom Smorgasbord shot. And we'll do that once get a bunch of people with their cameras on. And then after we do that, we'll have a break probably till about 15 minutes, about 5 after the hour. We'll make up a little bit of time. And because I think we'll try to keep the poster presentation short. And then, so we're getting a bunch of people I see with cameras on, so we'll take a picture in a minute. And then I'm actually gonna, while we go to break, people can leave, I'm gonna show you how to do the breakout rooms for a minute. So let's get, I think we're getting close to a picture if we wanna do that. So everybody smile and we'll do a couple of quick screenshots. So 1, 2, 3.
It's actually nice to see so many people. Better than the icons.
All right. So what I'm going to show you now is I'm going to open quickly. So we'll come back at 5 after the hour, whatever hour it is for you. Keep everybody, let everybody have a break. I'm going to open a couple of breakout rooms, and you should be able to see them now. And what you can do is you should be able to maneuver yourself into a breakout room. And you can just basically go to either my room or Ming-Wai's room and you can join it. And then when you get in there, you should be able to leave the room and you'll come back to the main room, but don't leave the meeting because there'll be an option when you see it's where the end thing is in the lower corner. So I see a couple people, you can start moving into the rooms and you can join them. And then when you do that, you can then explore coming back out. And then I also can send a message to everybody saying, great. Once people do that, I can broadcast a message that'll tell you that we're going to break until 5 minutes after the hour. So you can experiment with that for a few minutes, and then we'll all come back and we'll do the poster presentation starting at 5 after the hour, and we'll have everybody lined up and ready to go. So thanks everybody to the talks, and you can play with this, and then we'll see how that goes.
Okay, welcome back. I guess I'm wondering if somebody can help me by displaying the slides. If somebody else has the poster slides, I have them, but it's going to take a little bit of time from. I don't know that I can create the breakout rooms to do the poster slides and just show my screen at the same time. I can.
I'm Yang. I'd like to help to share the slides. I'm
so,
Yang.
So Andrew, Yang is from Nanyang University, and he's going to help you.
Okay. So why don't we get started if you want to put.
Great, Yang. Thank you. Okay. So let's try to get this going quick, and then the sooner we do this, the sooner we can get into the posters. So again, I see Jan's there. If people can turn on their camera and then also take themselves off mute just before the next person finishes, and I will try to keep everybody on time and give you a warning, but I think everybody can do this in 1 minute. So normally, if we were in person, I'd be giving prizes of cookies or food or donuts or beer to everybody who stays on time. But unfortunately, I can't do that. So go ahead, Steve.
But you can control switching the slides.
But we can control switching the slides. So after 1 minute, I'll probably start to say next slide repeatedly. So, okay. All right. So Jan, take it away.
Hello, everyone. Thank you. I will explore the response of flower trade cumulus clouds to 21st century climate change. The satellite image top left shows a transition from the sugar cloud state to the flower cloud state. And the lower left panels show the simulated transition in present day conditions, 2020, and in end of century conditions, 2095. Now, you will notice that at the end of the century, the size and the number of these flower clouds are significantly reduced. And I will discuss the mechanism that causes this suppression of the flower clouds. And I will identify the primary cause of this suppression, which is downwelling long-wave radiation from higher anthropogenic greenhouse gases at the end of the century. I will show that this long-wave radiation weakens the mesoscale circulation that is responsible for the flower clouds, which causes these flower clouds to form and which maintains them. Thank you.
Great. Next slide, please. Mark.
Good day, everyone. In the lower left-hand panel here, you'll see the intermediate stage of the stratocumulus to cumulus transition process, which is known collectively as cumulus-coupled stratocumulus. And in that phase, we have cumulus clouds that develop beneath stratocumulus and rise up into them, recoupling the stratocumulus above, and hence the name cumulus-coupled stratocumulus. Back in the early 90s, during the Aztecs experiment, it was noticed that when we have this cumulus-coupled stratocumulus, it tends not to occur in a random fashion, but rather has a mesoscale component of organization, hence leading to the term mesoscale boundary layer convective complexes. So what we are trying to do is use ENA observations as a baseline. We're using 4 years of summertime observations on that front to try to understand the thermodynamic environment in which we observe cumulus-coupled stratocumulus and how that is represented in, for example, the ERA5 reanalysis. And we're also coupling that with high-resolution WRF simulations. And over here on the right-hand side, you can see a slice from one of the simulations that we've done in which we reproduce these structures. And because of the model output, we have the ability now to sort of dissect what the organizing principles of these structures may be.
Thank you. Next slide.
Hi, everyone. So this work is based on the idea that the code of action cannot really produce really decoupled clouds because of the cumulus convection here. They can produce cumulus coupled cloud regime. Because of this, we proposed a hypothesis that the real unambiguous decoupling between the clouds and the ocean surface could only happen when you have a warm air vacuum. And this hypothesis has been proved by our previous observational work, which has been published. And to further test this hypothesis, we ran idealized large simulations, which is showing the lower left. So we have found that when you start with the well-mixed cloud top boundary layer with full cloudiness, the clouds in the warmer vacuum could maintain overcast for a much longer time than the clouds in the colder vacuum. And this leads to the conclusion that the real unambiguous decoupling between cloud and ocean surface during warm air vacuum could prolong the lifetime of the low-lying cloud decks. But that's it.
Andrew, I think you mute yourself.
Sorry, Nurun, are you there? No? No.
Hello, everyone. This is the present ongoing work.
Can you go to the next slide?
Hello?
Yes.
Yeah, this is our ongoing work on the dilution on the continental shallow cumulus case from the CAPEX observation. And the large eddy simulations are made here with the 10-kilometer horizontal and 4-kilometer vertical top with the 20-meter vertical grid resolution, which is able to resolve the rotating vortices around the moist plume structure here. And therefore, the entrainment rates are calculated for the different LEA sensitivity by changing the CCN concentration here. And it shows that high CCN concentration are associated with the high entrainment rates. Also, we have segregated the cloud core and the subsiding shell by means of a clustering technique. And the entrainment rates are also calculated for the same. So it shows that the cloud core has a least entrainment rate. So yeah, that's it. Thank you.
Great. Thank you. Guyong, next slide, please.
Hi. My name is Guyong Wen. This talk is focused on how to use the surface ground-based spectrometer to observe the aerosol properties in a cloud field. So we use alias model simulate the cloud field and use a 3D radio transfer model to simulate the ground-based shortwave radiometer observations. So basically, so as you can see, the top three sides is liquid water path, and the radians at 0.47 and 0.55 microns, and the bottom are the zenith radians just for clear. And for those two bands, and you can see the zenith radians 3D effects are really big, and especially for short wavelengths. But if we take the ratio of these two radiances, the cancels all those 3D effects almost, and that's we could use that to get the Armstrong exponent, because the optical depth is proportional to the radians. And we plan to use the arm-based ground observation to get optical size aerosol size inside the cloud field. Thank you.
Thank you. Next slide, please. This is Jianying.
Hi, this is Tianying. And first, I wish to acknowledge my advisor, Professor Zhanqing Li, and the significant contribution of Dr. Yutong Zheng as a co-author. In this work, we use remote sensing tools to determine the coupling of continental clouds with the surface. This method also can be used to retrieve the boundary layer height under cloudy conditions. As we know, the cloud surface coupling is an important process for the cloud and boundary layer development. This process has been extensively investigated for marine clouds. However, there is a lack of sufficient investigation for the cloud surface coupling over the land, partly due to more complex thermodynamic structure. Thus, we will use the LiDAR techniques and the surface meteorological data to address this issue. As a general objective, we wish to use this method to improve our understanding of cloud surface coupling processes over land. For the dataset part, we will use the amper measurement from LiDAR and the suite of surface meteorological measurement in the SGP site for about 20 years, from 1998 to 2019. As a result, we have developed a method to simultaneously retrieve the boundary layer height and the cloud surface coupling during the daytime. And we found that the cloud surface coupling and the boundary layer height derived from our method are highly consistent with those derived from radio sound. I hope to discuss the result in more details in the breakout room. Thank you.
Thank you. Next slide.
Hello, everyone. This is Jian Hao. In this study, we're trying to understand how does large-scale meteorological factors affect albedo susceptibility. And the key finding here is that meteorological covariabilities matters in terms of governing the albedo susceptibility, and more importantly, this covariability, the role of covariability varies from region to region. So the figure on the left is showing the albedo susceptibility as a function of cloud top height and free troposphere relative humidity. And you can see this is one, you merge all the covariability in this global analysis. And if you break into individual stratocumulus regions, which is showing in the middle, and you can see distinct features of this covariability manifest out. You can see that albedo susceptibility is showing different for different parts of the meteorological states. And even further, if you look at the right-hand side figure, and can see 4 meteorological factors covary differently for each stratocumulus regions, and this leads to quite different monthly evolution in the albedo susceptibilities. That's it. Thanks.
Thank you. Next slide, please.
Oh, okay, this is Xinwang. Can you hear me?
Yes.
Okay, thank you. Okay, today we are going to talk about the hidden large aerosol-driven cloud cover effect over high latitude ocean. Previous studies show negligible cloud cover effects during the Iceland volcanic eruption in 2014. Generally, cloud fraction is sensitive to aerosol in the global scale, so why changes in aerosols didn't cause cloud cover effects and the similar meteorological conditions between volcanic year and background years. To address this question, we built prediction model, and based on the model, we calculate ND ratio and cloud fraction ratio, and found cloud fraction ratio increasing when ND less than 99. And then the cloud cover stopped to grow and shows a saturated status. ND increasing during the eruption compared with that of the background years mainly happened with ND greater than 99. Evident cloud cover effect with a relative increase of 12% was found before its approaching saturation. So to sum up, it's necessary to account for the background ND and the saturation of ACI to avoid possible underestimation. Thank you for your attention.
Thank you. Next slide, please. Ko Yamasaki, go ahead.
Hello. In this study, we used an ADS model to examine how injected aerosols influence mixed phase clouds and how its key process varies depending on environment. The simulations are performed for two observation-based cases with different environmental conditions, which were used in previous LDS interim comparisons. For each of them, sensitivity experiments are conducted to vary the number concentration of INPs to simulate various cloud phase partitioning and to switch on and off CCN emissions. The upper and lower left figures show a snapshot of albedo and the concentration of injected CCN in one case. Results show that the responses of cloud albedo to CCN emission are smaller in clouds with more ice than those containing less ice for both cases. The right figures show fractional changes between cases in which CCN emissions are switched on and off. Although increase in LWP is weaker and response in effective particle radius is more positive in clouds with more ice for both cases, processes responsible for the cloud responses are found to differ between the cases. Thank you.
Thank you. Next slide, please.
All right.
Paloma?
So I'm Paloma, and the motivation behind this study is that warm clouds are a predominant source of uncertainty in climate models. And this is partially because of the covariability of the different processes influencing warm rain. So here, warm rain was defined using in connection with the warm clouds, and each cloud was reduced to one value in order to have an independent data set of all the different observations. So here, the plot that I'm showing is basically from one analysis that we did using multilinear regression and random forest models. And we use these models to be able to disentangle the role of the different factors. And we see somewhat expected a relationship, like for cloud duration, depth, and liquid water path in the top panels, where we see that rain rate is expected to be affected by these variables in a positive manner. And when we look at CCN in the bottom left, we basically see that it is not a predominant factor and that the magnitude of its impact is highly variable. And for turbulence in the other two plots is basically showing that it depends where it is measured, with cloud turbulence at cloud base being an important factor in suppressing rain rate, and turbulence at cloud top not having a clear signal. So this shows a potential method to isolate each signal. And in particular, when we're looking at signals that are not predominant factors, such as turbulence and CCN. And I'll be happy to talk more about this in the breakout. So thank you.
Thank you. Next slide.
So hello, my name is Roland from Leibniz Institute for Tropospheric Research. And I have a few slides available that demonstrate the use of our cloud microphysical model, Cosmos Specs. It's coupled to a numerical weather prediction model. And I've done a few applications where we exchanged the CCN and INP fields and had a little bit of sensitivity studies on that, in particular when it comes to precipitation formation and the interplay of the different treated microphysical processes. And here you see on the right particular the liquid water content, ice water content, and as an example, the rhyming tendency that plays here a role in the cases that we investigated.
Thank you. And I think that's the last slide, but I think, Steve, you wanted to talk about your poster, but you didn't have a slide.
Oh, I don't need to well, since you give me a minute, I'll mention it.
You get a minute.
All right. I was going to have well, anyway, what I was going to mention is that in the Combo field experiment, which is for cold air outbreaks over the Northern Atlantic, Greenland and Norwegian seas, we've done simulations of that. And we found some interesting transitions, or actually maintenance of open cells. But these open cells have, I don't think they've been previously reported because they're obscured by the mixed phase clouds and the snow, and they're not easily visible by geostationary satellite and so on. But they actually undergo the same sort of life cycle that the open cell clouds that were reported by Graham and his cohorts back in 2010, associated with cold pools. So anyway, that'll be reported in upcoming meetings later this summer. So AMS meeting and the GWEX meeting. So.
Okay. So Steve, do you have a room you want to talk about this in or no?
No, that's okay. I'd like to talk to some of the other people. So,
okay.
But anyone can talk to me about it if they want. Just message me. So
fine.
Thanks.
Okay.
Thanks for the plug.
So I'm going to open breakout rooms now, and you can stop sharing. Thanks very much for everybody, all the poster presenters, and keeping on time. And we'll do about, maybe cut it a little short so we have some time for discussion, but something like 13 or 14 minutes, and I'll announce for changing over. And so I'll open these rooms. Everybody can assign themselves to the different breakout rooms. Pick the one by name that you would like to actually go to. And then after about half the time, so maybe 13 or 14 minutes, I'll send a message that we can encourage people to switch rooms. You can stay in the room if you want, but I'd encourage people to go. So again, you see how to do it. Once you've joined, you come back by hitting leave room, and make sure you leave the breakout room, not the meeting. So we just have to make sure that we do that. So anyway, enjoy, and hopefully this goes well. If you have any questions, come back to the main room, and there'll be somebody here, myself or Elizabeth, who can answer questions. So I see lots of people moving, so that's great. See everybody joining some of the breakout rooms. So please, based on those posters, pick some a talk that you might want to, somebody you might want to talk a little more about, and something you might want to hear a little bit more about as well. See everybody's moving over, so that's good. Great.
I see that even some of the presenters are not going to their own room, but maybe they're not here.
Yeah, they may have taken a break. So the presenters should go to their rooms if they can. I actually can assign them, I guess, right?
There. Yes, then when they come back, they would be in their room.
So I did that. Whoop. I think there were 2 of them, that was it. There we go.
And one person is in the meeting twice, which is, they must be on 2 different devices.
Yeah, that's probably the case. So
it's weird.
Yep. All right, I'm going to join one of the breakout rooms for a bit that has only 1 person. So
yeah, I'm going to hold the fort down here.
Okay, thank you. All right, it turned out he wasn't there. But it looks like pretty much everybody's moved over, so that's great.
Yeah, I just see three people. 4.
Right, but one of them was listed twice, so I think that's a second device at least. Some of those actually might be double devices. Oh, I didn't start a timer, did I? That's a problem. Well, let's see. I want to do about probably 13 minutes. So 13 minutes on the second one. Let's leave 5 minutes at the end.
Yeah, I see I sent my chat at 9:24. So if that, or yeah, 9:24. So if that
9:24.
That was
Okay.
right before you opened them.
Okay, so they've been open for 5 minutes. All right, so we'll probably do, we do 37 and 50. That's 13 minutes each, right?
Mm-hmm. It's never long enough, so it's definitely not, there's no magic to it.
Right. Okay, so we'll give everybody 7 or 8 more minutes. But it looks like it's working.
Yeah, everyone was able to join on their own, which is good.
Yeah.
And so we're still streaming. Will there be some kind of wrap up at the end that you want to still be streamed?
There probably will be.
Okay.
So
I would just leave the stream open then.
okay, we'll just leave the stream open for a half
Yeah,
hour.
you can't really stop it and start it. It then shows up as two separate.
Something else. So okay,
streams.
yeah, that's the only downside of this. But I guess I could. Can I pause the recording?
I did pause the recording.
Oh, you did, right? Because it says resume. So I have to remember to do that when we go to break. When we go to the posters, is to pause the recording. So
Yeah, then at least the file is smaller, and I think that Ryan can swap it out. You know, if it winds up that you want the shorter recording on YouTube.
oh, on YouTube. Oh, yeah. Okay, I didn't realize we could do that, but we'll see. I don't know how much people are using it in the end, but it's sort of making it available.
Yeah, and they can just always fast forward. That's easy enough to do.
Right. All right, I might dive into one of these groups then and see how things are going.
Sure. Yeah, I'll be right here.
So, okay, thanks. Find another one. Which one was the one I go to? Let's try. Okay, let's see if people come back. I guess they don't have to come back to the main room, right? They can, or do they have to?
They don't have to. In previous versions of Zoom, they did.
Oh, they can just hit breakout rooms and then join.
They can just, yeah, move from room to room on their own, which does make things easier.
I see people are, I'll tell them that. I see people are jumping around, that's good. Lots of people jumping in and out, so that's good. We'll have to see how this goes. I haven't tried this before. I don't know if you've tried it before.
Moving from room to room?
Yeah, no, I mean the whole concept of doing posters like this.
Yes, it's exactly how we did the CESM poster session.
Okay.
Last June, we had 22 posters and people came and went. And
Okay. How long was that session? Just out of curiosity.
Over an hour.
Over an hour. What was the feedback on that?
Yeah, people liked it, and then we had the lobby, so people would come and chat in the lobby, and then go off to a poster and come back.
Okay, I guess if it's an hour, it's longer. That works out a little easier.
This is a really good, test session reminder to see how I might want to streamline it. We really just modeled it over being in the lobby and having people stop by, and we did have the posters, images of the posters online in advance.
Okay. Yeah, I think the other option, which probably works, is, and I've done this for some other meetings, which is getting better, is the gather.town interface, which allows you to physically move between rooms.
Yeah. Yeah, I saw when SciParks did, or I guess it was all of the UCAR interns did their posters last year, and I hopped in and gave that a try. It was sort of like the learning curve was a little bit awkward, and you could hear people. And
yeah, we did a meeting. I was in a NOAA meeting that was actually much better. I mean, I used it at the beginning of the pandemic, and it's really improved.
Oh, good.
So it's actually somewhat usable, but you can set up rooms, and then you basically can make places where everybody is supposed to be in the same location, and then they actually can talk to each other. So I think it has actually improved significantly, obviously, because they've had a lot more use. So
yes.
So it looks like we're getting pretty good distribution.
Everyone's in a room.
Yeah, that's good.
Yeah, some people are by themselves.
Yeah, I might jump into the one that has one person in it for a little bit.
Two that have a really big crowd.
Yeah.
Does anyone have any questions?
So Elizabeth, how do I kill the breakout rooms? And do they kill right away, or do I?
No, you.
Oh, you get
you
60
can
seconds.
Send them a message, and then it usually gives them a time.
Yeah. Okay.
Depends on. Oh, there you go. You got 1 minute. Yeah.
There. Okay. No,
Mhm.
that'll happen. So, all right, I was a little slow, but that's okay.
Yeah, it has to do with the settings that are done in advance.
Yeah, that's fine. Now I know. So I see everybody coming back. So.
I'll go ahead and resume the recording.
Okay, thank you. So we'll try to close on time in like 10 minutes.
We see a very strong suppression of clustering. We see fewer and smaller flower clouds, and also fewer cold pools. So the question here is, what is going on? Yes.
Now we're all back.
Okay. Good. That was quick.
That was quick. And we can take some comments as to whether that was too quick or not, but we figured we'd try it, give everybody a taste of how that would work. So thank you. We now have, we'll try to wrap up in the next couple of minutes for any discussion or summary or thoughts that people had. I don't know, Matt and I have not had much of a chance to talk about this. I don't know if Matt wants to make any comments, or if there's anything that you saw, Matt. I thought there was quite a bit of interesting stuff. I thought obviously I think some of the two major topics were entrainment and analysis of warm rain formation as a function of aerosols. And what I really liked some of the more, I think there was some really interesting stuff, both from modeling and satellites, that potentially we could try to bring together. And I also thought the analysis of the adiabatic fraction was interesting and a little bit scary because it seemed pretty low over most of the low cloud regions. And so we're trying to use drop number for some of these retrievals that would be affected, or liquid water path would be affected by the adiabatic fraction. That seems like it might be a little problematic. So I don't know if there were comments or thoughts on any of that.
Maybe it's a bit underestimated because the cloud top CW was used. If you use something that is more representative of the mean CW of the cloud, it will be a bit higher.
Yeah.
But still, it goes precipitously low when the cloud becomes deeper. So that's it's a major problem anyway.
Well, when the cloud becomes deep, isn't that due to loss by precipitation?
The clouds keep entrainment from cloud base as they go high, and eventually they evaporate. So, so there is a upper limit of the plume that can goes up without some forcing that arrange clouds to protect each other, and then they can break this upper limit. I think that what is shown is the upper limit here for non-organized clouds.
Okay.
So Danny, isn't it the case that if you want to get the cloud depth, you need the clouds to be broken? So you're looking more at cumulus clouds here, right? More than stratocumulus, or am I wrong?
We took only scenes in which we could somehow get the cloud base through some different depths of the clouds, and the cloud base should be more or less flat.
Yeah.
So we have the distribution of the LiDAR echoes as a function of height, and that gives us the cloud depths.
Yeah, so in that sense, it's not all that surprising that the adiabatic fractions get quite low.
We take the highest 10 percentile of the clouds. That is, we focus only on the cloud cores for MODIS, the LWP of the highest 10 percentile.
Matt, you have any other comments that you wanted to make, things that you saw?
Yeah, I thought we had a lot of great presentations, and it was really excellent to sort of see the time evolution element appearing in several of these talks, looking at cloud state transitions and the different drivers, such as the inversion strength and height, and these different methodologies to compute the liquid warpath and CD&C relationships. Zibo Zhang's presentation was really great. So I don't have anything specific to mention on that, just some passing thoughts.
Okay. Yeah, I'm just trying to think with the group if there's ways to start to bring, because one of the functions of ACPC is to try to bring some of this together and cross-pollinate ideas and see where we can make progress. So, I mean, thinking about, we've seen observations and modeling studies, thinking about what we can do from the other side to actually either, test the models with observations more, or look at the observational analysis in models too. I mean, I think I'm going to get back in touch with Zibo about trying to get him some modeling data to take a look at. I think there's some other opportunities there too in some of what we saw.
I think that there is a nexus between cloud adiabatic fraction, cloud cover, and cloud feedback that now we have. We are on the way to get good observations for that, and it calls for simulations of the same, and also the sensitivity to aerosols. And these are the key issues of the low cloud ACPC questions.
I think that's true, Danny. I think that the risk, though, is that we have to, it would be useful to make sure that we're being comprehensive, because with some of the methods, if we're focusing on cores or we require broken clouds for the scenes, then I just worry that there's some systematic sampling errors, but we certainly could sample the models in the same way. And we've done some analysis of this in the last year or two as well. Any other thoughts? Or Ming-Wai, I don't know if you had any other thoughts as well.
Thank you. Not much. I'm thinking about the modeling effort. I think we see a lot of the good observational studies, and also some of the AES type of studies. But then when we come to cost model, say, because I think eventually we want to use those observations to confirm the model. It seems that there are gaps. I think either resolution, like global models, I think it's really hard. Say how meaningful when we run global models, try to test, or even regional models, some cost resolution to test those. I'm still trying to figure out what's the best strategy to really use or learn from this process level understanding of studies. Try to use that to advance modeling study. I feel that the progress is pretty slow in recent years for cost say like to improve models. But I do not have any concrete ideas for what is the best approach for us to do that.
Okay. Well, one approach that we've been using for a long time, but is the Lagrangian approach. Once you identify a cloud system in a larger scale model, then follow it with a LAS type model, and you can use higher resolution than that. I mean, I think everyone knows that, but it still is a very useful method. I really like seeing the mesoscale LAS. I mean, those are just fascinating to see the cloud organization as well as the small scale structures.
Yeah, the self-organization is key to the cloud fraction, which could be very, very vastly different if you allow for the self-organization or not.
Yes, yes.
Yeah, I want to follow on Minghua's point on the modeling. I feel, we do a lot of LES model simulations. However, in the global model, which is IPCC used, and looks like we'll give up. There's a large biases in similar to the stratocumulus cloud, which cause a lot of bias in the radiative forcing and also aerosol indirect effect. One talk from Jensen's group, which is about how the entrainment depends on droplet normal concentrations. This is interesting. In the global model, I don't think this is considered. The entrainment parameterization in either in cloud or in the deep convection parameterization, both they don't have these dependencies. So the errors impact will not be considered. And that would be some good observations to further develop parameterizations for global model.
So Jiwen, do we know what the mechanism is to parameterize it? The effect of drop number on entrainment?
Well, the simplest way, basically, you can see the observations can derive some relationships. Maybe just put some adjustment of the entrainment by the droplet number. So right. Just some simplest trying, and then from there we can see how strong global model would respond to that.
Right. We tried a little bit of that with Trudy Stillermo's group in Norway, but maybe it wasn't done in the right way. And there's other ways to do that, more focused on entrainment than evaporation, which is what we were doing. But I do think it's a good way forward is to try to think about that. And I guess we're going to wrap up soon. There's one comment from Yutong that, Johannes is leading this project to look at ACI across the major GCMs. And I think that may show some promise. He's got some interesting results, I think, that are going to be out pretty soon that he's going to be talking to us about too, at least to some of the modeling groups about, I know. Any final thoughts, or we're getting just to the top of the hour to our time to stop. Mingwai, do you want to close it for today and have any other final comments?
No, not much. I think we're going to continue tomorrow. I think there's will be a lot of more interesting talks there too.
Right. So we'll have more interesting talks, and we should also have some time for discussion tomorrow. So I think with that, we will say good night, especially to Mingwai and everybody else who's staying up really late. We appreciate that. And good afternoon, and still good morning for many of us, for those who had to get up early. So thanks again. We had up to 96 participants today. So I think that's great. And we'll see everybody tomorrow.
Thank you, Andrew. Bye-bye, everyone.